Hello there, and welcome to the Sleepy Space Channel. There are places in the universe so extreme that the mind has no honest handle on them. There is a star so dense that a single spoonful of it would weigh as much as a mountain. There are magnets strong enough to unmake the atoms of a body from a distance, edges from which not even light can return, and a cold so complete that it sits a single degree above the lowest temperature there is. These are real places, scattered across the dark, and tonight we travel to the most extreme of them, one careful and unhurried stop at a time. If you find these quiet explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next couple of hours, none of this is anything you need to carry. Every one of these places is unimaginably far away, indifferent and unreaching, turning quietly in the dark. So settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. There is a kind of place in the universe where matter itself has been pushed past every limit we understand. It is a place where the ground beneath you would not be ground at all, but something stranger, denser, and more silent than anything our world contains. To begin this tour, we travel to the surface of a neutron star, one of the most extreme objects ever found. It is a sobering thing to consider, and for the first few minutes, we will let that weight sit with us before the night softens it into something quieter. A neutron star is what remains when a giant star dies and its core collapses. In that collapse, the protons and electrons of ordinary matter are crushed together until almost nothing is left but neutrons, packed shoulder to shoulder with no space between them. The result is a sphere only about 20 kilometers across, no wider than a single city, and yet it holds more material than the entire sun. It is the densest object we can see anywhere in the cosmos. The numbers are difficult to hold in the mind. A single sugar cube of neutron star material brought to Earth would weigh about 1 billion tons. That is the weight of a mountain, folded into something you could hold in your hand. The matter is so tightly bound that the rules of everyday life simply stop applying. Nothing on our world is built this way, and nothing on our world ever could be. The gravity at the surface is the part the mind refuses to picture. It is roughly 100 billion times stronger than the gravity you feel right now. An object dropped from a height of only 1 meter would strike the surface traveling thousands of kilometers per second. Under such a pull, the star pulls itself into an almost perfect sphere, smoother than any object polished by human hands. There are mountains on a neutron star, but they are not mountains as we know them. The crust is a solid lattice, thought to be many billions of times stronger than steel. And yet the gravity is so severe that the tallest peak it can hold rises only a few millimeters above the surrounding ground. A whole mountain range, flattened to the height of a coin. The star is, in its own way, the most level place that exists. Many neutron stars also turn at speeds that seem impossible. A young one can spin tens or even hundreds of times every second, carrying its enormous mass around with it each time. The fastest known turns about 700 times in a single second, its surface moving at a sizable fraction of the speed of light. Some sweep beams of radio waves across the sky as they turn, and from far away we receive them as a steady, patient ticking. The interior is a place our physics can only approach with caution. Beneath the crust, the neutrons may flow as a frictionless fluid, a superfluid that moves without resistance. Closer to the surface, the matter may be squeezed into long shapes that scientists have nicknamed nuclear pasta, sheets and tubes of nuclear material with no equal on Earth. we will likely never see these layers directly. We know them only through reason and through the faint signals the stars send out. When a neutron star is first born, its surface can shine at around 1,000,000 degrees, glowing in a light our eyes cannot see. Over long ages, it slowly cools, settling into the quiet of the surrounding dark. It does not hurry. It has nowhere it needs to be. It simply turns and cools and waits on a timescale that makes a human life feel like the blink of a far-off light. And here, already, the first softening begins. For all its severity, a neutron star is also one of the most peaceful objects imaginable. It is smooth, it is balanced, it is steady. It has been spinning quietly in the dark since long before the sun first lit, and it will go on spinning long after. It asks nothing of us. It threatens nothing that we love. It is simply there, far away, turning in the silence, a small, bright remnant of a star that lived and died before our world began. The way we find these objects is itself worth dwelling on. Many neutron stars send out narrow beams of radio waves from their magnetic poles, and as the star turns, those beams sweep across space, like the light of a slowly rotating lantern. If one of the beams happens to pass over the Earth, we receive a brief pulse, once each turn, with remarkable regularity. From far away, a spinning neutron star announces itself as a steady, patient ticking in the dark, one of the most precise rhythms known anywhere in nature. That rhythm is so dependable that these stars rank among the finest clocks the universe contains. Some of the fastest ones keep time across years more steadily than many clocks built by human hands. Now and then the ticking shifts very slightly, a tiny stutter in the rhythm, and we believe these small changes come from the star's interior settling, the superfluid within, slipping against the solid crust above it. Even the cracks and adjustments of such a star are gentle, measured things, played out across the quiet. It is hard to hold the density of these objects in the mind, so it helps to try a comparison. If every human being who has ever lived were gathered together and compressed to the density of a neutron star, the entire crowd would fit inside a single drop of liquid. The gravity is so strong that it bends the path of light near the surface, which means that, standing upon one, you would see slightly around its curve, taking in a little of the far side as the light wrapped toward you. Time itself would run slower there than it does for us, slowed by the weight of all that gathered mass. These remnants do not stay frantic forever. Over long ages, the spin gradually slows, the surface cools, and the beams grow faint until the star settles into a quiet and almost undetectable old age. Some are spun back up by a companion star feeding material onto them, set turning hundreds of times a second once more, but most simply wind down, turning slower and dimmer through the ages. They are, in the end, among the most steadfast objects in existence, keeping their long, slow time in the dark. The story of how these objects entered our knowledge is a quiet one, and it carries a gentle charm. When the first regular pulses were detected arriving from a fixed point in the sky, ticking with such precision that they seemed almost manufactured, the astronomers who found them were genuinely puzzled. For a brief time, before the true explanation was understood, the steady signal was half-jokingly noted as something that might, conceivably, be a beacon from somewhere far away, so unnatural did its regularity seem. The truth turned out to be stranger and more beautiful than any beacon. The ticking came from a spinning remnant of a dead star, sweeping its beam across space, keeping a rhythm so faithful that it rivaled the finest clocks. What had seemed at first like a message was instead the simple turning of a small, dense star, patiently announcing itself across the light years. Many thousands of these objects are now known throughout the galaxy, each one keeping its own steady time, a scattering of faithful rhythms turning quietly in the dark. There is a delicate balance that lets a neutron star exist at all, and it is worth noticing. As the core of a dying star collapses, the neutrons resist being squeezed any further, and that resistance is what holds the star up against its own enormous gravity. But this support has a limit. If the remnant is too heavy, beyond roughly 2 to 3 times the mass of the Sun, even the packed neutrons cannot hold, and the collapse continues until a black hole forms instead. A neutron star, then, is a thing balanced on a knife's edge, just massive enough to crush ordinary matter out of existence, and just light enough to stop short of disappearing entirely. It sits, quietly, at one of the most finely poised thresholds in all of nature, holding itself steady against gravity for ages without the slightest strain. So we let the neutron star rest where it is, the densest ground in the universe, level and quiet and impossibly far. And we turn now to something stranger still, a close cousin of the neutron star whose true extreme is not its weight, but the unseen force that surrounds it. Among the neutron stars, there is a rarer kind, and it carries the strongest magnetic field ever found anywhere in the universe. It is called a magnetar, and its power lives not in its surface, but in the invisible field that wraps around it. If a neutron star is a study in weight, a magnetar is a study in force, the kind of force that reshapes the very structure of matter. Every magnet you have ever held has a field measured in modest units. The Earth itself is a magnet, and its gentle field is what turns a compass needle toward the north. A magnetar's field is roughly 1,000 trillion times stronger than the Earth's. The number is so large that it slides past comprehension, which is exactly why this place belongs on our tour. It sits at the far edge of what nature allows. A field that's strong does not simply push and pull. It begins to change the things it touches. Within a few thousand kilometers of a magnetar, the field would distort the atoms of any ordinary matter, stretching them out of their round shapes into thin rods. The familiar chemistry that holds a body together would quietly come undone, not through heat or impact, but through the silent pressure of magnetism alone. It is one of the few places where a field of force, by itself, would dissolve the rules of ordinary substance. The energy stored in that field is enormous, and from time to time the star releases some of it at once. The crust of a magnetar can crack in a sudden shift, a kind of starquake, and the field snaps into a new arrangement. When this happens, the star sends out a burst of high-energy light across the galaxy. A single great flare can briefly shine brighter in that kind of light than every other star in the Milky Way combined. One such burst reached us from a magnetar tens of thousands of light-years away. Even after crossing all that distance, it carried enough energy to gently disturb the upper edge of Earth's atmosphere, the thin layer where our air meets the dark. It did no harm. It simply registered, a faint touch from a remnant unimaginably far away, a reminder of how much power can be folded into a single small star. Magnetars are young, as these things go, only thousands of years old. Their fierce fields are not permanent. Over time, the field decays, and the star settles toward the calmer life of an ordinary neutron star. Only a few dozen are known to us. They are brief and uncommon, the most intense magnets the universe will ever make, and then they quietly fade. It is worth pausing on how far away all of this is. The nearest magnetars lie thousands of light years from us, separated by an emptiness so wide that their power, for all its scale, spends itself harmlessly into the dark between the stars. What reaches us is only the faintest signal, a slow pulse, a soft flicker recorded by patient instruments. The force that could unmake matter at close range arrives here as a whisper. It is worth asking where such a field comes from, and the answer lies in the violence of the star's birth. When a magnetar forms in the collapse of a giant star, the newborn remnant may spin extremely quickly and churn within, and this rapid early motion can wind its magnetic field up to tremendous strength, like a dynamo running far past anything ordinary. The field that results is locked into the star, far stronger than the rotation alone could ever explain, a reservoir of energy waiting in the structure of the star itself. That stored energy is what makes a magnetar restless. The intense field puts the rigid crust under enormous strain, and from time to time the crust yields, shifting in a sudden small adjustment. The field then snaps into a new arrangement, and the energy released pours out as a flash of high-energy light. Most of these flashes are modest, brief flickers repeated over time, which is why some magnetars are known as repeating sources of soft gamma rays. But on rare occasions, the release is enormous, a single giant flare carrying more energy in a fraction of a second than the sun gives off across many thousands of years. The strength of the field is difficult to set against anything in daily life. The strongest magnets built by human hands, the ones used in medical scanners, are powerful enough to tug at metal across a room. A magnetar's field is many trillions of times stronger than that. Brought near one, ordinary matter would not simply be pulled. It would be reshaped at the level of its atoms, the gentle round clouds of its electrons stretched into long thin needles, the chemistry that holds substances together quietly rewritten by the field alone. For all this, the magnetar phase does not last. The fierce field gradually decays, and as it does, it warms the star from within and slowly fades. Within a span of thousands of years, the magnetar quiets toward the calmer life of an ordinary neutron star, its great field spent. They are brief visitors then, the strongest magnets the universe will ever build, flaring for a short while in the long history of the cosmos before settling into stillness. It is sometimes said, to give a sense of the field's reach, that a magnetar brought even as close as the distance of the moon would disturb the magnetic strips on every card and the workings of every device across the Earth, all without a single sound. That is only a thought experiment, of course, for the nearest magnetars lie many thousands of light-years away, far beyond any such nearness. But the image captures something true about the nature of this place. Its power is not the power of impact or heat, but of a silent, invisible field, reaching out and quietly reordering matter at a distance. It is a reminder that the most extreme forces in the universe need not be loud or violent at all. Some of them are perfectly silent, felt only in the way they rearrange the world around them, and most of the time spent harmlessly into the empty dark. So the magnetar, too, finds its place in the quiet. It is the strongest magnet in creation, and also one of the most solitary, turning alone in a far region of the galaxy, its great field slowly settling towards stillness. We do not need to fear it. We need only notice it, the way you might notice a distant light on a far shore, and then let it go. And from the remnants of dead stars, we turn now to a star that has not yet died, but is living out its final ages, a giant so large that it has no surface to stand on at all. Some of the most extreme places in the universe are not remnants, but living stars, and the largest of them are almost beyond belief. These are the red hypergiants, the most swollen stars known. If one were set down where the sun now sits, its glowing outer edge would reach past the orbit of Mars, and in the largest cases, beyond the orbit of Jupiter. The inner planets would lie deep inside the star itself. The scale is hard to translate into anything familiar. The largest of these stars measure more than 1,000 times the radius of the Sun, and the very biggest may reach 1,500 times. Light, which crosses from the Sun to the Earth in about 8 minutes, would need hours simply to travel from one side of such a star to the other. They are the largest single objects of their kind that the universe builds. And yet, strangely, they are not solid or heavy in the way their size suggests. Their outer layers are spread so thin that, near the surface, the gas is less dense than the air in a laboratory vacuum. A hypergiant is a red-hot near-emptiness, an enormous glowing cloud held loosely together by gravity, its true substance gathered far down toward the center. To stand on its surface would be impossible, because there is no surface to find, only a slow thickening of light and gas as you fell inward. The reason these stars belong on a tour of extremes is what happens in their final ages. A massive star lives by fusing light elements into heavier ones in its core, and for most of its life it fuses hydrogen into helium, calmly across millions of years. But near the end, it begins to burn through heavier and heavier fuels, each stage faster and hotter than the last. Helium becomes carbon, carbon becomes neon and oxygen, and the pace quickens with every step. The last stages are astonishingly brief. Where hydrogen burning lasts for ages, the fusing of silicon into iron may last only a day or two. In that final stretch, the core temperature climbs past 1 billion degrees. The star is racing now, consuming its remaining fuel at a tremendous rate, building toward a moment it cannot avoid. And the trouble is that iron is the end of the road. Iron cannot release energy by fusing further. When the core becomes iron, the fire that held the star up simply goes out. What follows is the collapse, and we will come to that next. But it is worth resting for a moment on the star itself in these final ages before the end. It hangs in the sky as one of the most enormous objects in existence, shedding its outer layers in slow, uneven breaths, wrapping itself in shells of dust and gas it has cast off over time. From a distance, it would appear as a great red lantern, dim and immense, glowing softly against the dark. There is something almost gentle in the way these giants live out their endings. They do not rush toward us. Their violence, when it comes, is the violence of light and heat and time turned inward upon themselves, in a place so far away that we can study it only as a faint point in the night. The largest stars in the universe are also among the loneliest, burning quietly through their last ages in distant corners of distant galaxies. To picture the true size of these stars, it helps to walk outward from something familiar. The Sun is already enormous, more than 100 times the width of the Earth, large enough that 1 million Earths could fit inside it. Yet the largest hypergiants are more than 1,000 times wider still than the Sun. Place one where the Sun now sits, and its glowing edge would swallow the orbits of the inner planets entirely, reaching out toward the giant planets in the cold beyond. A single star, occupying the space where a whole inner solar system once turned. The surfaces of these giants are not smooth and steady like the face of the Sun. They churn with enormous cells of rising and falling gas, each one larger than the orbit of a small planet, boiling slowly as heat rises from below. Because the outer layers are bound so loosely, the star breathes in and out, swelling and shrinking over long cycles, and from time to time it sheds great clouds of its own material into space. Around many of these stars we find shells and veils of cast-off gas, marking the slow loss of the star's outer self. There is a reason such enormous stars live such short lives. A star burns brighter and hotter the more massive it is, and the brightest stars pay for that brilliance by consuming their fuel at a furious pace. Where a modest star like the Sun will shine steadily for 10 billion years, a giant may live only a few million before exhausting itself. They are the brief, brilliant lives of the stellar world, blazing enormously and ending quickly, their whole existence a small fraction of the age of quieter stars. In their final stages, the layered burning inside them takes on a structure like the rings of an onion, each shell fusing a heavier element than the one outside it, all the way down to the iron-forming core. The pace of each stage is quicker than the last, the final ones lasting mere days, as the star races toward the moment its fuel runs out. It is a quiet kind of urgency, hidden inside an object so large that, from outside, it appears only to glow and slowly dim, giving no outward sign of the swift changes within. The deep red color of these giants is itself a sign of their nature, and it carries its own quiet beauty. A star's color reveals its surface temperature, and these enormous stars, for all their size, have surfaces that are relatively cool, glowing in shades of orange and red rather than the white or blue of hotter stars. The heat they pour out comes not from a fierce surface, but from their sheer enormousness, the great area over which even a cool glow adds up to tremendous light. Some of them visibly dim and brighten over time as their loose outer layers swell and shrink, and as clouds of dust form and clear around them. To the patient eye, such a star is never quite still, breathing slowly across the years, a soft red beacon marking a life in its final unhurried chapter, far across the reaches of the galaxy. So we leave the giant where it hangs, red and immense and softly fading, in the final calm before its collapse. And we follow it now into the single moment that ends it, one of the brightest events the universe has ever produced. When the iron core of a giant star fails, the collapse is among the most powerful events in all of nature. The center falls inward in less than a second, and what happens next, for a few short weeks, can outshine an entire galaxy of hundreds of billions of stars. This is a supernova, and it sits near the top of any list of the universe's extremes. The collapse begins when the core can no longer hold itself up. Gravity, which the star has resisted its whole life, finally wins. The core falls inward at a fraction of the speed of light, and in that fall it reaches such density that it abruptly resists, rebounding outward in a tremendous shock. The outer layers of the star, falling inward behind the core, meet this rising shock and are blown outward into space. The energy released is difficult to state in ordinary terms. A single supernova pours out more energy in a few seconds than the Sun will produce across its entire 10 billion year life. Most of that energy is not even carried by light. It is carried away by neutrinos, the faint and almost weightless particles that stream out of the collapsing core in an enormous flood, passing through the rest of the star and through space and through worlds, almost without touching anything at all. The shock wave itself races outward at speeds of 10,000 to 30,000 kilometers per second, a few percent of the speed of light. At the blast, temperatures climb into the billions of degrees. In that furnace, the lighter elements of the dying star are fused and forged into heavier ones, and many of the heavy elements that exist anywhere in the universe trace their origin to moments like this one. This is where the tour turns towards something quieter and more personal. The calcium in your bones, the iron in your blood, the oxygen you are breathing as you rest, much of it was made inside stars and scattered into space by explosions like these. A supernova is the most powerful detonation in nature, and it is also one of the great acts of creation. The dying of giant stars is the reason small worlds like ours have the materials to exist at all. It is fair to wonder whether such an event could ever reach us, and the honest answer is reassuring. A supernova would need to occur quite nearby, within perhaps 25 to 50 light-years, to seriously affect our world, and there are no stars close enough and ready to do so. The giant stars capable of this lie far away, separated from us by the enormous gulfs between the stars. We watch their endings as points of light that brighten and slowly fade, harmless across the distance. What a supernova leaves behind is itself remarkable. At the center, the collapsed core remains, either a neutron star, like the one we visited, or, for the largest stars, a black hole. Around it spreads an expanding cloud of glowing gas, the scattered outer layers of the star, lit from within and drifting outward for thousands of years. These remnants are some of the most graceful structures in the sky, slow-blooming clouds of color marking the place where a star once ended. The flood of neutrinos deserves a moment of its own because it is one of the strangest features of the whole event. Neutrinos are particles so faint and so reluctant to interact that they pass through ordinary matter almost as if it were not there. Streams of them are passing through your body right now, from the sun, without your ever feeling them. In a supernova, the collapsing core releases them in numbers beyond counting, and they carry away the great majority of the energy, racing outward through the dying star before the visible blast has even begun. The light that we eventually see tells its own slow story. In the days after the collapse, the supernova brightens steadily as the shock reaches the surface and the outer layers are lit. Then, over weeks and months, it fades, its glow sustained by the slow decay of freshly forged elements within the expanding cloud. By watching how the brightness rises and falls, astronomers can read what kind of star it was and how it ended, long after the event itself has passed. A single point of light, brightening and dimming, becomes a record of an entire star's death. These endings are also the great forges of the cosmos. The ordinary fusion inside stars builds elements only up to iron. Everything heavier requires more violent conditions, and the supernova provides them in the searing pressure and heat of the blast and its aftermath. The atoms scattered outward seed the surrounding space with the ingredients of future worlds, and over long ages those ingredients gather again into new stars, new planets, and, on at least one small world, into living things that can look up and wonder where they came from. So a supernova is not only an ending, it is a link in a long and patient chain, the means by which the material of one generation of stars becomes the material of the next. Each one enriches the dark around it a little more, passing its forged elements onward into the slow recycling of the galaxy. The most powerful explosions in nature are, across the long view, simply the way the universe stirs its ingredients and begins again. These events are not as rare as their power might suggest, though they remain comfortably distant. In a galaxy the size of ours, a supernova occurs on average a few times each century, scattered among its hundreds of billions of stars. Long ago, before anyone understood what they were, people on Earth occasionally noticed a new point of light appear in the sky, bright enough in a few cases to be seen even in daytime, lingering for weeks or months before slowly fading from view. They were watching distant stars end their lives, the light of those endings arriving after journeys of thousands of years. Each new star that appeared and faded was the calm, far-off announcement of a giant's death, and of the fresh scattering of elements into the dark, the slow seeding of the galaxy with the makings of new worlds. So the most violent explosion in the universe turns out to be, seen from far enough away and long enough after, a slow and quiet thing, a spreading cloud, a scattering of the very atoms that make worlds and bodies and breath. We are, in the most literal sense, made from the calm ash of these distant fires. And we carry that with us as we move on, toward an event rarer still, where not one dead star, but two come together. Sometimes a star does not die alone. Many stars are born in pairs, two suns bound together, circling a shared center for the whole of their lives. And when both of those stars are massive enough to end as neutron stars, something rare and extreme becomes possible. Two of the densest objects in the universe can find themselves locked in orbit, slowly drawing closer, until at last they meet. The approach is unhurried, almost beyond imagining. The two neutron stars circle each other for ages, but as they turn, they very slowly lose energy, and their orbit gradually tightens. Across millions of years, the gap between them narrows, the circles grow smaller, and the two stars wheel faster and faster around their shared point. The final stage, after all that patience, takes only seconds. In those last moments, the two stars are whirling around each other hundreds of times per second, and they begin to stir the shape of space itself. Mass in motion sends out ripples in space-time, gravitational waves, spreading outward at the speed of light. As the stars spiral together, these ripples grow stronger and quicker, carrying away the last of the orbit's energy until the two remnants finally touch and merge. The waves that result travel across the entire universe. By the time they reach us, after crossing distances measured in many millions of light years, they have faded to something almost unmeasurably small. They stretch and squeeze the space around us by less than the width of a single proton. And yet we have learned to feel them, using instruments of extraordinary patience, listening for the faint tremor of two dead stars meeting in a far-off galaxy. The merger itself is a furnace beyond anything else on this tour. For an instant, matter is heated and compressed past the conditions found at the center of any star. In that brief and extreme moment, a remarkable thing happens. The collision forges a large share of the universe's heaviest elements, the gold and platinum, and the rare metals that are difficult to make any other way. A single merger can produce many times the mass of the Earth in precious metal alone. This is the part worth holding gently in mind. The gold that exists anywhere, in rings, in coins, in the fine threads of our machines, was very likely made in events like this, in the meeting of two dead stars long before the sun was born. The most extreme collision the universe can stage is also the origin of some of the quietest and most familiar treasures of our small world. Violence, once again, turns out to be the maker of gentle things. After the merger, what remains usually collapses within moments into a black hole, and around it spreads a glowing cloud lit by the freshly made elements as they settle and decay. This afterglow, called a kilonova, shines across many kinds of light for days before fading. It is one of the few events in the cosmos that we can detect both as light in the sky and as a tremor in the fabric of space, two different senses meeting on the same distant event. And then it is over, and the sky returns to its long quiet. The collision that shook the shape of space, that made gold out of ruin, settles into a small dark remnant and a slowly cooling cloud. It happened unimaginably far away, in a galaxy whose light is older than our species. It reached us only as the faintest of signals, and it left behind, scattered into the dark, the raw material of things we will one day hold in our hands. The gravitational waves these mergers produce are worth lingering on, because they are a genuinely new way of sensing the universe. For most of history, everything we knew of the cosmos came to us as light of one kind or another. But these ripples are not light at all. They are ripples in the shape of space itself, the actual fabric in which everything sits, stretching and squeezing ever so slightly as they pass. When two dead stars spiral together, they set that fabric trembling, and the trembling spreads outward in every direction at the speed of light. To catch such a ripple is an act of almost unreasonable patience. By the time the wave from a distant merger reaches us, it stretches the space around us by an amount smaller than the width of a single proton, a change so tiny it seems impossible to notice. And yet, with instruments of extraordinary delicacy, we have learned to feel it, to register the faint passing tremor of an event that happened in a far-off galaxy ages ago. We have, in a real sense, learned to listen to the universe as well as look at it. The making of heavy elements in these collisions answers a question that puzzled scientists for a long time. The lighter elements were accounted for by ordinary stars and by supernovae, but the origin of the heaviest, the gold and platinum and the rare metals, was harder to explain. The merging of dead stars provides exactly the conditions needed, a sudden flood of particles in unimaginable density, building the heaviest atoms in moments. A single such event can forge many times the mass of the Earth in precious metal, scattered outward into the dark to drift for ages. When two neutron stars merge, the result is often a brief and brilliant cloud, glowing from the decay of all those newly made elements, shining across many kinds of light at once, for a few days before it fades. It is one of the rare events we can sense in more than one way, feeling its tremor in space and seeing its glow in the sky, two different senses confirming the same distant happening. After that, the sky returns to its long quiet, and the new elements begin their slow drift through time. There is something quietly moving in the long patience these collisions require. Two stars are born together, live out their separate lives, and die as dense remnants, and only then does the slow work of the final approach begin. For millions, sometimes billions of years, the two remnants circle each other, drawing imperceptibly closer with each turn, losing the faintest trace of energy to the ripples they send into space. The whole of human history would pass in such a system without any visible change at all. And then, after all that waiting, the end comes in a handful of seconds, a brief and brilliant meeting that scatters the makings of treasure across the dark. The most extreme collision the universe stages is also one of its most patient events, an embrace ages in the making, finished in a moment, leaving behind something that will drift quietly for the rest of time. So we let the two dead stars rest where they finally met, and the gold drift outward on its long journey through time. And we turn now to the narrowest and most concentrated burst of energy the universe knows how to make. Of all the extreme events in the cosmos, the most luminous are also among the briefest. They are called gamma-ray bursts, and for a few seconds at a time, a single one can be the brightest thing in the entire observable universe. They are not steady places so much as moments, narrow beams of energy fired across the dark and then gone. A gamma-ray burst is born in the most violent endings the universe stages. Some come from the collapse of an especially massive star into a black hole. Others come from the merger of two dead stars, like the one we just visited. In either case, the collapsing center forms a black hole, and around it, matter is funneled into two narrow jets that fire outward from the poles, traveling at more than 99.99% of the speed of light. The energy carried in these jets is difficult to set against anything familiar. In a span of seconds, a single long burst can release more energy than the sun will produce across its whole life of 10 billion years. Because the energy is focused into a narrow beam rather than spread in every direction, it reaches across enormous distances, and we detect bursts from billions of light years away, from a time when the universe was young. That narrowness is the key to why these events, for all their power, are not a source of worry. A gamma-ray burst is like the beam of a far-off lighthouse. Its light is concentrated into a thin cone, and that cone is almost never pointed anywhere that matters. The sky is enormous, the beams are narrow, and the chance of one aimed directly at us from nearby is so small as to be, for all practical purposes, nothing at all. It is true that if such a beam were aimed at Earth from within our own galaxy, it could affect the thin protective layer of our atmosphere. But the conditions required are rare. The alignment must be nearly perfect, and the suitable stars lie far away. Across the long history of our world, life has continued through everything the sky has done. The beams fire, again and again, out into the dark, and the dark simply absorbs them, far from anything living. What we receive instead is something almost serene. A burst flares somewhere in a distant galaxy, lasting from a fraction of a second to a couple of minutes, and then it fades into a long, slow afterglow that may linger for hours or days. To our instruments, it appears as a brief brightening at the edge of sight, a signal from an ending that happened billions of years ago, finally arriving now. There is a kind of comfort folded into that delay. The light we catch from these bursts left its source when the universe was a fraction of its present age. The stars that made it are long gone, their galaxies transformed. We are not watching a present danger. We are reading an old letter, sent across more time than our minds can truly hold, telling us only that the universe, long ago and far away, did something extraordinary. There are, in fact, two kinds of these bursts, and they come from different endings. The longer bursts, lasting from a few seconds to a couple of minutes, are thought to come from the collapse of certain rapidly spinning giant stars into black holes. The shorter ones, lasting less than a second or two, are believed to come from the merging of dead stars, the very kind of collision we visited a moment ago. Two very different events, at opposite ends of the lives of massive stars, both able to produce the same searing beam. The reason the energy is concentrated into a narrow jet, rather than spread in all directions, comes down to the machinery at the center. As the collapsing core forms a black hole, matter swirls around it and is channeled along the poles, squeezed into two tight streams that fire outward in opposite directions. Confined this way, the energy is focused like the beam of a spotlight, rather than the glow of a bare lamp, which is why a single burst can be seen clear across the observable universe, from a distance of billions of light years. Because that light has traveled so far, these bursts are also a kind of window into the early universe. When we catch one from many billions of light years away, we are seeing an event that happened when the cosmos was young, its light only now arriving after an enormous journey. The most luminous events in nature double as some of our oldest messages, carrying news of the distant past, of stars that died before our galaxy had taken its present shape. After the initial flash, a burst does not vanish at once. It leaves behind a fading afterglow, a softer light that lingers across many kinds of radiation, slowly dimming over hours and days as the jet plows into the thin gas around it. By studying this afterglow, astronomers can measure how far away the burst was and what kind of event produced it. The brilliant blade of light gives way to a gentle, fading ember, and then to darkness, far away and long ago. It helps to hold the geometry of these beams clearly in mind, because it is the reason they are no cause for concern. A gamma-ray burst does not shine in all directions at once. Its energy is squeezed into two narrow cones, each pointed a particular way, and the rest of the surrounding sky receives nothing at all. For one of these cones to matter to us, it would have to be aimed almost exactly along the line toward Earth, from a suitable star close enough to reach us, an alignment so improbable that across the long history of our world, it has remained, for all practical purposes, simply nothing. The beams fire out into the dark again and again, and the dark, in its enormousness, absorbs them harmlessly, far from anything that lives. For a long time, these bursts were a genuine mystery, noticed almost by accident. Instruments set watching the sky for entirely different reasons began to record brief flashes of high-energy light, arriving from no fixed place, lasting only seconds, then gone. At first, no one knew how far away they were, or what could possibly cause them. Only after years of patient study did it become clear that they came from billions of light-years away, from the deaths of distant stars and the mergers of remnants in far-off galaxies. The realization was a quiet kind of wonder, that these faint flickers, so easy to miss, were in fact among the most powerful events the universe had produced since its beginning, their light only now arriving after an enormous and ancient journey across the dark. So the most luminous events in all of creation reach us as the gentlest of flickers, brief points of light that brighten and fade in the night. They are the universe clearing its throat in a far room, ages ago, the sound only now drifting in. We note them, and we let them pass. And from these blades of distant light, we turn to the places where light itself can no longer escape. There is one kind of place in the universe so extreme that even light cannot leave it. A black hole is a region where matter has gathered so densely, and gravity has grown so strong that space and time themselves are folded steeply inward. At its boundary lies the most absolute edge in nature, a place from which nothing returns. And yet, as we will find, it is also one of the calmest places the universe contains. A black hole forms when a great mass is packed into a small enough space. The collapsed centers of the largest stars can do this, and so can the giant black holes that sit at the centers of galaxies. Once enough mass is concentrated, the pull near it becomes so steep that the speed needed to escape rises beyond the speed of light. And since nothing travels faster than light, nothing can climb back out. That threshold has a name. It is called the event horizon. The event horizon is not a surface in the ordinary sense. There is nothing solid there, no wall, no shell, nothing to touch. It is simply a boundary in space, the precise line beyond which escape is no longer possible. For a black hole with the mass of the Sun, this boundary would be only about 6 kilometers across. For the giant black hole at the center of our galaxy, it spans something like 24 million kilometers, large enough to hold many suns within it. The strangest part is what happens to time near this edge. As an object falls toward the horizon, an observer watching from a safe distance would see it move more and more slowly, its light stretching toward red, its motion seeming to freeze just at the boundary. Time itself runs differently in such steep gravity. From far away, the falling object never quite arrives. It appears to hang there, dimming, slowing, fading, held at the edge of the dock. For the one who falls, the experience would be different, and here the picture grows gentler than expected. Near a small black hole, the difference in gravity between your head and your feet would be severe, stretching anything that fell in. But near a truly giant black hole, the edge is so broad and the curvature so gradual that crossing it would feel like nothing at all. There would be no wall, no jolt, no moment of crossing. The most absolute boundary in the universe could be passed without noticing it had been passed. It is worth setting aside one common idea, because it is not true. A black hole is not a current that pulls things in from far away. It does not reach out and sweep up the sky around it. From a safe distance, a black hole behaves like any other mass. If the Sun were somehow replaced by a black hole of the same mass, the Earth would not be drawn in. It would continue in its same orbit, in the same year, around a center that simply no longer shines. it took a long time for anyone to believe such a thing could be real. The idea emerged first from the mathematics of gravity, as a strange solution that seemed almost too extreme to exist in nature. For decades, it was treated as a curiosity, a quirk of the equations, rather than a description of anything out in the sky. Only gradually, as the evidence gathered, did it become clear that the universe truly does make these objects, and makes them in great numbers, from the collapsed centers of giant stars to the enormous ones that anchor the centers of galaxies. We cannot see a black hole directly, since it gives off no light, but we can see what it does to everything around it. Gas falling toward one heats and glows before it crosses the edge. Stars near one are pulled into swift, tight orbits that reveal the unseen mass at their center. And in recent times, we have even managed to capture an image of the glowing ring of light bent around the edge of a giant black hole, a dark circle outlined by the radiance of matter swirling just outside it, the closest we have come to a portrait of the unreturning edge. The stretching of time near the horizon is one of the strangest and most beautiful features of these objects. The steeper the gravity, the more slowly time runs, and near a black hole the effect grows extreme. If you watched a clock fall toward the edge, you would see it tick more and more slowly, the light from it stretching toward red, until it seemed to hang frozen at the boundary, never quite crossing. From the clock's own point of view, however, time would run perfectly normally, and the edge would be passed without any pause at all. It is worth holding on to the gentleness of crossing a large one, because it overturns the usual picture. We tend to imagine the edge of a black hole as a place of sudden violence, but for the truly giant ones, the boundary is so broad and the curvature so gradual that there would be no wall to strike, no jolt, no sign at all that the most absolute threshold in the universe had been crossed. The terror lives entirely in the idea of the place, not in any moment one would actually experience there. There is a further gentleness in the long fate of these objects, one that makes them seem less permanent and forbidding. Black holes are not truly eternal. Across spans of time so enormous they dwarf the present age of the universe many times over, a black hole very slowly gives off the faintest trickle of energy, gradually losing mass, until in the unimaginably distant future it may fade away entirely. The smallest ones would fade first, the giants last of all, but the principle is the same. Even the most absolute objects the universe makes are, on a long enough view, temporary, quietly winding down across timescales beyond all imagining. The edge from which nothing returns is itself, in the end, slowly returning to the dark from which it came, with a patience that puts every other slow thing to shame. So the most extreme edge in the universe is, in its own way, the most still. Nothing escapes it, but nothing about it is hurried, and nothing about it is reaching toward us. The nearest black holes lie far away, turning quietly in the dark, bending the light of distant stars in slow and graceful arcs. They are the places where motion finally comes to rest, where even light lies down. And that brings us to the one question this edge leaves hanging, the question of what lies beyond it. It is the one place in the universe our knowledge cannot follow, and we approach it now, gently, as the next stop on our tour. Beyond the edge of a black hole lies the one place in the universe we genuinely cannot describe. Everywhere else on this tour, however extreme, our physics still has something to say. We can write down the density of a neutron star, the field of a magnetar, the energy of a supernova. But past the event horizon, our finest theories begin to fall silent, and what waits at the center remains the most honest mystery we have. Our best theory of gravity does make a prediction, and it is a strange one. It says that at the very center of a black hole, All the matter is drawn to a single point of unlimited density, a place called a singularity. But most physicists do not read this as a true description of reality. They read it as a signal that the theory has reached its limit. When a set of equations produces infinity, it usually means the equations are no longer complete, that some deeper understanding is missing. That missing understanding has a name, even if we do not yet have the theory itself. To describe the center of a black hole, we would need to combine our science of the very large, which governs gravity and space, with our science of the very small, which governs particles and forces. These two great descriptions of the world have never been fully joined. The inside of a black hole is one of the few places where both would matter at once, and so it remains beyond our reach. Strange things happen even before the center. Once past the horizon, the relationship between space and time appears to change places. Outside, you may move freely through space, but are always carried forward in time. Inside, moving forward in time means moving inevitably inward toward the center. The fall becomes as unavoidable as tomorrow. There is no direction that leads back out, not because the way is blocked, but because every direction leads further in. There is also a riddle here that has occupied careful minds for a long time. When matter falls into a black hole, the detailed information about what it was seems to vanish from the universe. This troubles physicists, because in every other situation, such information is thought to be preserved. Whether it is truly lost, or hidden, or somehow carried away, is one of the deepest open questions in all of science. The black hole keeps its secret, and we keep asking. It is tempting to find all of this unsettling, the idea of a place where knowledge simply stops. But there is another way to hold it, and it is the gentler way. Not every mystery is a threat. Some are simply the quiet edges of the map, the places where the known world fades softly into the unknown. For all of human history, there have been such edges, and we have lived peacefully alongside them, content to let some questions remain open. The center of a black hole is the farthest of these edges, and also the most untroubling. It lies sealed behind a boundary that nothing crosses outward, in objects scattered far across the dark. Whatever happens there happens entirely out of reach, asking nothing of us, affecting nothing we touch. It is a door left honestly ajar, and we are free to leave it that way. There is a further idea, gentle and unproven, that softens the picture of an endless, crushing center. Many physicists suspect that the singularity our equations predict is not truly real, but a sign that something we do not yet understand takes over at the smallest scales. In place of a point of unlimited density, there may be some new state of matter or geometry, held together by laws we have not yet written. We simply do not know, and the honest answer is that the center of a black hole is hidden from us in a way nothing else in the universe is. The puzzle of the lost information has occupied some of the most careful thinkers for a long time. In the world we can observe, the detailed history of things is never truly erased, only scrambled. Yet matter that falls into a black hole seems to take its history with it, beyond any reach. Over time, ideas have emerged that the information might somehow be encoded at the very edge, or carried away slowly as the black hole itself changes across enormous spans of time. The question remains open, a quiet riddle at the boundary of our understanding. It helps to remember how completely sealed this mystery is. Whatever happens beyond the horizon happens behind a boundary that nothing crosses outward, not light, not matter, not any signal at all. The inside of a black hole is not merely far away. It is causally separated from us, unable to reach us even in principle. Nothing that occurs there can affect the world where you are resting now. It is the most thoroughly isolated place imaginable, walled off not by distance, but by the very shape of space and time. And so the inside of a black hole becomes, of all the places on this tour, the one we can hold most lightly. We cannot study it, cannot reach it, cannot be touched by it. We can only acknowledge that it is there, sealed and silent, keeping the one secret the universe has hidden most completely. There is no need to solve it tonight, or ever. It is enough to know that the cosmos still holds a few questions in reserve, and to let them be. There is one more idea that gently rearranges how we picture the inside, and it is strangely soothing. Once past the edge of a black hole, the center is not really a place off in some direction, the way a destination lies ahead on a road. It is better understood as a moment in the future, something that lies in time rather than in space. Inside the horizon, reaching the center becomes as unavoidable as reaching tomorrow, not because the way is forced, but because all the directions one might travel lead there in the end. It is less like falling toward a wall and more like the simple, quiet arrival of a later hour. Whatever waits there waits not at the end of a journey through space, but at the end of a stretch of time, hidden from us, as completely as the far side of a moment we will never reach. So we let the inside of the black hole keep its silence, the one address in the cosmos our science cannot visit. There is a kind of rest in that, in admitting that not everything is ours to know. And we turn now from the black holes that sit still to the ones that wander, drifting alone and unseen through the spaces between the stars. Not every black hole sits quietly at the center of a galaxy or in a steady orbit with a companion star. Some of them wander. They drift alone through the spaces between the stars, dark and silent, carrying no light of their own, crossing the galaxy on long and lonely paths. They are among the hardest objects in the universe to find, precisely because there is so little to see. A wandering black hole is usually born from the death of a massive star, the same kind of collapse that can leave a neutron star behind. But the explosion that forms it is rarely perfectly even. The slight imbalance can give the new black hole a kick, a push in one direction, sending it drifting away from where its parent star once lived. Others are flung outward by close encounters, slingshot by the gravity of passing stars until they are cast loose to travel on their own. Once adrift, such a black hole becomes almost invisible. It gives off no light. It has no glowing disk, no companion to mark its presence. It is simply a region of intense gravity moving through the dark, and unless something passes very close to it, there is almost nothing to reveal where it is. For a long time, these drifting remnants were only expected in theory, suspected to be out there, but never clearly seen. We have found a way to detect them, and it is a quietly elegant one. When a dark, massive object passes almost directly in front of a more distant star, its gravity bends the star's light, acting like a lens. For a time, the distant star appears to brighten and shift, warped by the gravity of the unseen object crossing in front of it. By watching this slow brightening and fading, astronomers identified a lone black hole drifting through space, betrayed only by the way it bent the light behind it. The numbers suggest there are a great many of them. Our galaxy has hosted countless massive stars across its long history, and each one that ended in this way may have left a remnant behind. Estimates point to 100 million or more black holes drifting through the Milky Way, most of them dark and unaccounted for, wandering the long roads between the stars. The galaxy is quietly full of them. It is natural to wonder whether one of these dark travelers might find its way to us, and here the enormous emptiness of space becomes a comfort rather than a worry. The distances between stars are so immense that even a galaxy full of wandering black holes almost never has one come near anything. The nearest black holes we know of lie more than 1,000 light-years away, and none of them is on any path toward us. They wander, but they do not arrive. If you could somehow stand and watch one pass at a safe distance, you would see very little. There would be no roar, no pull, no sense of menace. You might notice only a small region of the starfield behind it, seeming to ripple and shift as its gravity bent the passing light, a brief and silent distortion, and then stillness again as it continued on its way. It would move through the dark the way everything moves through the dark, patiently, indifferently, alone. The method that revealed one of these wanderers is worth describing slowly, because it is a quiet kind of detective work. Gravity bends the path of light, and a massive object, passing almost exactly in front of a distant star, will act like a lens, gathering and focusing that star's light, so the star appears to brighten over a span of time, then fade as the object moves on. Most of the time, the lensing object is itself a faint star, and a small extra glow betrays its presence. But in one careful case, there was a brightening with no visible object behind it at all, the unmistakable signature of something dark and heavy drifting silently across the line of sight. Working out that such an object was truly a black hole, rather than a dim star, took years of patient watching. Astronomers tracked the slow shifting of the background star's apparent position as the dark mass crossed in front of it, measuring an effect so small it strained the limits of what our instruments can detect. From that tiny shift, they could weigh the unseen object and conclude that it was too heavy to be anything but a black hole, traveling alone through the dark. A single lonely remnant, found not by its light, but by the gentle warping of light from far behind it. The sheer number of these objects follows from the long history of the galaxy. Over billions of years, countless massive stars have lived and died, and a share of them ended as black holes. Many of those were kicked loose by the unevenness of their birth, or cast out by close encounters and set adrift to wander. Estimates suggest the Milky Way may hold 100 million or more such drifting remnants, most of them dark and untraceable, threading the spaces between the stars on their own long, slow paths. For all that number, the galaxy is so enormous that these wanderers almost never come near anything. The distances between stars are measured in light-years, in the trillions upon trillions of kilometers, and a black hole crossing that emptiness is unimaginably unlikely to pass close to any particular star or world. They are not gathering, not converging, not drawn toward the bright places. They simply drift, each one alone, through an ocean of distance so wide that their isolation is nearly complete. It is worth dwelling on just how mistaken the common picture of a black hole is, because the truth is so much calmer. We tend to imagine these objects as currents that pull everything around them inward, sweeping up the sky. But a black hole's gravity is no greater than that of any object with the same mass. A wandering black hole drifting through space does not reach out and gather the stars around it. It simply moves on its own path, bending the light of whatever happens to lie almost directly behind it, and otherwise leaving the surrounding dark untouched. If one were to pass at a safe distance, the nearby stars would barely register its presence, continuing on their own quiet courses. The dark traveler is not a hunter at all. It is only a piece of the galaxy's slow, ordinary traffic, crossing the enormous emptiness alone. So the wandering black holes drift on, 100 million quiet travelers crossing a galaxy so wide that their solitude is nearly perfect. They are not hunting. They are not approaching. They are simply part of the slow traffic of the cosmos, dark shapes moving through an ocean of distance. And from these lonely wanderers, we turn now to the opposite extreme, the single most crowded place in the entire galaxy. We have visited black holes that sit alone and black holes that wander. Now we travel to the place where the largest black hole in our galaxy resides, and to the remarkable region that surrounds it. At the center of the Milky Way lies a supermassive black hole, and around it is gathered one of the most densely packed fields of stars anywhere in the galaxy. After all the loneliness of the wandering remnants, this is a place of extraordinary closeness. The central black hole holds about 4 million times the mass of the Sun, and yet all of that is packed into a region smaller than the orbit of Mercury. It does not shine. We cannot see it directly. We know it is there because of the stars that circle it, stars whose motions reveal an enormous unseen mass tucked into a small space. By watching them swing around an empty-seeming point, astronomers traced the shape of the giant that holds them. Those nearby stars move in a way that is hard to picture. The closest ones travel around the black hole at thousands of kilometers per second, swept along on tight orbits that they complete in a matter of years, where our own Sun needs hundreds of millions of years to circle the galaxy once. They race around the dark center like moths around a lamp, their paths bent into long, fast loops by the gravity of the unseen mass. The crowding of stars in that region is the part that strains the imagination. In the space of a single light year near the center, stars may be packed, perhaps 1 million times more densely than they are around the Sun. Here at home, the nearest star is more than 4 light-years away, a lonely distance. There, the night sky would be filled with close, brilliant suns in every direction. So many and so near that true darkness would never fall. The sky would always glow. It is not a calm region in other ways either. The center of the galaxy is bathed in high-energy light and threaded by powerful magnetic filaments, long, graceful strands stretching across many light-years. Gas swirls and falls and is occasionally torn apart as it nears the black hole. From time to time, the black hole flares as it swallows a little of this material, brightening briefly before settling back into quiet. For now, it is a gentle eater, taking in very little. And yet, even here, in the most crowded and energetic corner of the galaxy, the dominant quality is a kind of ancient steadiness. The stars are close, but they are not colliding. Their orbits are fast, but they are stable, settled into patterns that hold for ages. The black hole is enormous, but it is calm, turning slowly at the center of it all, gathering its bright crowd of stars around it like a still point at the middle of a wheel. All of this lies about 26,000 light-years from us, near the center of the galaxy we call home. We sit far out in the quiet suburbs, on a single ordinary star, looking inward toward that bright and crowded center across an enormous gulf of space. We are close enough to study it and far enough to be perfectly safe. The center blazes and turns, and out here, the night is dark and still. The way astronomers came to know this hidden giant is a story of remarkable patience. The center of the galaxy is wrapped in thick clouds of gas and dust that block ordinary light, so the region cannot be seen with the eye or with an ordinary telescope. But certain kinds of light, in the infrared and in radio waves, can pass through that veil. Watching in those kinds of light over many years, astronomers tracked individual stars looping around an invisible center, and from the shape and speed of their orbits, they measured the mass of the thing they circled. The stars themselves drew the portrait of the unseen giant. Some of those stars come astonishingly close to the black hole on their tightest passes, swinging around it and then racing back out on long, stretched orbits. At their nearest approach, they move at a sizable fraction of the speed of light, whipped around the dark center and flung outward again, only to return years later for another pass. Watching them is like watching comets circle a sun, except that the sun is invisible and weighs 4 million times as much as our own. Their faithful, repeating loops are among the clearest evidence we have that the giant is truly there. The crowding of stars near the center would make for a sky unlike anything we know. Out here, on our quiet edge of the galaxy, the nearest star is more than 4 light-years away, a single point of light in a dark sky. Near the center, stars may be packed perhaps 1 million times more closely, so that the sky in every direction would be filled with bright, near suns. Night, in the way we understand it, would never truly come. There would always be light, a sky crowded with brilliance, and at its center a single point of perfect dark. And yet, for all its closeness and energy, the central region holds an ancient steadiness. The stars are near one another, but they are not colliding. Their orbits settled into patterns that hold across enormous spans of time. The black hole at the center is enormous, but for now, it feeds only lightly, flaring softly now and then, as a little gas falls in, otherwise turning in quiet. Even the busiest place in the galaxy keeps a slow and patient rhythm, measured not in moments, but in the long turning of ages. It is worth remembering, as we picture this blazing center, just how far we sit from it, and how that distance is its own kind of shelter. Our sun lies roughly 26,000 light-years from the center of the galaxy, far out along one of the spiral arms, in a calm and unremarkable region. The crowded center, with its million close stars and its silent giant, is something we can study only across that enormous gulf. On a dark night, looking toward the constellations of the southern sky, the combined glow of all those distant central stars appears as a soft, hazy band, the brightest stretch of the Milky Way. We see the most crowded place in the galaxy not as a danger, but as a gentle smear of light, a faint cloud arching overhead, 26,000 years old by the time it reaches our eyes. So we leave the crowded center to its slow and ancient rhythm, 4 million suns of mass and 1 million close stars, turning quietly at the middle of the Milky Way. And we follow that idea of a feeding black hole outward and back in time to the brightest, steady objects the universe has ever made. We have seen that a black hole, by itself, gives off no light. But when a giant black hole is feeding, the matter falling toward it can become the most luminous, steady source in the entire universe. These are the quasars, the brilliant centers of certain distant galaxies, and they shine with a brightness that is difficult to set against anything in ordinary experience. They are the brightest engines the cosmos knows how to build. A quasar forms when a supermassive black hole, like the one at the center of our galaxy, but often far larger, has a generous supply of gas around it. That gas does not fall straight in. Instead, it gathers into a flattened, swirling disk, circling the black hole at tremendous speed. As the material crowds and rubs together on its way inward, it heats to extraordinary temperatures, and it begins to blaze. The light comes not from the black hole itself, but from the brilliant disk of matter spiraling toward it. The amount of light produced is staggering. A bright quasar can shine with the power of 1 trillion suns, and it does this from a region not much larger than our own solar system. A single feeding black hole, in a space we would consider small, can outshine an entire surrounding galaxy of hundreds of billions of stars. For a long time, when astronomers first noticed these brilliant points, they could not understand how something so small could shine so brightly. The answer was the falling matter and the enormous gravity that drives it. The inner regions of the disk reach hundreds of thousands, even millions of degrees, glowing fiercely across many kinds of light. And many quasars do something more. From their poles, they fire twin jets of material outward at nearly the speed of light, narrow beams that can stretch far beyond the host galaxy, reaching across spaces larger than the galaxy itself. They are among the most powerful and far-reaching structures in all of nature. Here, though, distance and time once again turn power into peace. The brightest quasars lie billions of light-years away. The light we receive from them left its source when the universe was young, long before the Earth or the Sun existed. We are not seeing them as they are now. We are seeing them as they were in the distant past, and across all those billions of light-years, even 1,000,000,000,000 suns of brightness dwindles to a faint point, no brighter to the eye than a dim and ordinary star. There is a reason quasars belong mostly to the early universe. In those ancient times, there was more loose gas to feed the giant black holes, and so they blazed. As the ages passed and the gas was used up, most of these engines quieted. Many galaxies that once held quasars, including perhaps our own, now hold calm and silent centers. The brightest era of the universe is, in a sense, already behind it, its great fires banked low. It is even possible that the center of our own galaxy flared in this way in the far past, and may stir again in the far future if enough gas should fall inward. But that, too, is a slow and distant prospect, nothing that touches the quiet of any single night. The engine at our center sleeps, and the brilliant quasars of the early universe send us only their old, soft light. When these brilliant points were first noticed, they presented a genuine riddle. They appeared as faint, star-like specks, and yet their light, when measured carefully, showed that they lay billions of light-years away. For anything that distant to be visible at all, it would have to shine with almost impossible brightness, far more than any ordinary galaxy. The objects were named for their puzzling star-like appearance, and for a time no one could explain how something so small could pour out so much light. The answer, when it came, was the feeding black hole and the brilliant disk of matter spiraling toward it. The disk itself is a place of fierce motion and heat. Gas circling a giant black hole moves at a sizable fraction of the speed of light, and as it crowds inward, friction and pressure heat it to hundreds of thousands of degrees, even into the millions near the inner edge. At those temperatures, the disk blazes across many kinds of light at once, from radio waves through visible light and on into high-energy radiation. It is the brightest steady glow the universe produces, all of it from matter in its final spiral before crossing the unreturning edge. Many of these engines also fire enormous jets from their poles, narrow beams of material flung outward at nearly the speed of light. These jets can travel far beyond the host galaxy, reaching across spaces larger than the galaxy itself, ending in great glowing clouds where they finally plow into the thin gas between the galaxies. They are among the largest single structures the universe contains, and they trace, in light, the influence of a single black hole reaching out across an enormous expanse. The reason these brilliant engines belong mostly to the early universe is a matter of fuel. In ancient times, there was far more loose gas available to fall toward the giant black holes, and so they blazed. As the ages passed, and that gas was gathered into stars or used up, most of the engines quieted, their disks thinning, their light fading. The brightest era of the cosmos lies in its past, its great furnaces, now mostly banked low, sending us only the old light that left them when the universe was young. These distant engines turn out to be quietly useful to us, which softens their power into something almost helpful. Because a quasar shines so brightly from so far away, its light passes through enormous stretches of space on its way to us, crossing the thin gas that lies between the galaxies. That gas leaves faint imprints on the light, and by reading those imprints we can map the otherwise invisible material strung across the cosmos. A quasar becomes a kind of distant lantern held up behind the whole intervening universe, letting us trace the dim threads of gas we could never see on their own. The brightest objects ever made serve, in the end, as gentle beacons, lighting the way through the dark for those patient enough to read them, their ancient glow turned to a quiet kind of help. So the brightest objects ever made reach us as gentle points in the dark, ancient lanterns burning at the edge of sight, their fury long since softened by the journey. We could lie beneath them and never know their power. And from the brightest places in the universe, we turn now to the coldest and the emptiest, the quietest corners of all. So far, our tour has carried us through heat and density and force, the furnaces and the crushing remnants. But some of the most extreme places in the universe are extreme in the opposite way. They are the coldest and the emptiest places that exist, regions of such stillness that almost nothing moves at all. After the great engines and explosions, these are the universe at its most quiet. To understand cold in space, it helps to remember what temperature really is. Temperature is a measure of motion, of how quickly the tiny particles of matter are moving. When they move quickly, we call it hot. When they slow, we call it cold. And the coldest anything can ever be is the point where that motion nearly stops entirely, a limit called absolute zero. Nothing can quite reach it, but the universe comes remarkably close. Even the emptiest space is not perfectly cold, because the whole universe is gently warmed by a faint glow left over from its earliest times. This is the cosmic microwave background, the cooled remnant of the heat of the early cosmos, and it fills all of space evenly. It sets a kind of natural floor for the temperature of the universe, a little under 3 degrees above absolute zero. Everywhere you might go, this faint warmth follows, the oldest light there is. And yet there is a place colder even than that floor. When gas is made to expand quickly, it cools, the same way the air rushing from a can grows cold. In one particular cloud, gas streaming outward from a dying star has expanded so rapidly that it has chilled below the temperature of the background glow itself. It is, as far as we know, the coldest natural place in the universe, hovering around 1 degree above absolute zero, colder than the ancient warmth that fills the rest of space. Beyond cold, there is emptiness, and the universe holds emptiness on a scale that is hard to take in. Between the galaxies lie enormous regions called voids, great rounded spaces, hundreds of millions of light-years across, holding only a thin scattering of galaxies, or sometimes almost none at all. One well-known void stretches about 330 million light-years from side to side, an opening in the cosmic web so wide that light needs hundreds of millions of years simply to cross it. To stand within the center of such a void, if one could, would be to find oneself in a near-perfect solitude. The nearest galaxies would be so far away as to be barely visible, faint smudges scattered thinly across an otherwise empty dark. There would be no bright band of a home galaxy overhead, no crowded sky, only a quiet and immense openness in every direction. It is the loneliest geography the universe contains. Even the space between galaxies, away from the voids, is emptier than anything we can make. On average, intergalactic space holds about 1 atom in every cubic meter, a scattering so thin that no laboratory on Earth has ever produced a vacuum to match it. The universe, for all its bright places, is mostly this, an enormous and gentle emptiness, lightly dusted with the rare glowing islands we call galaxies. It would be easy to find such cold and such emptiness lonely, even fearful. But there is another way to see it, and it is the truer one. Cold in space is not a force reaching toward you. It is not a wind, not a presence, not something that hunts warmth. It is simply what remains when there is almost nothing left to move, the deep stillness of a place at rest. The great voids are not menacing. They are the quietest places in all of creation, where nothing stirs, where everything is finally calm. The way that one cloud became colder than the background glow is a small marvel of ordinary physics taken to an extreme. When a gas expands, it cools, because its particles spread out and slow down. You can feel a faint version of this in the chill of air escaping a pressurized can. In that distant cloud, gas is streaming away from a dying star so quickly and expanding so rapidly that it has chilled below even the faint warmth that fills the rest of space. It is a natural refrigerator on a scale no laboratory could match, the coldest spot we have ever found in nature. The great voids form through a slow and patient process across the history of the universe. In the early cosmos, matter was spread almost perfectly evenly, with only the faintest ripples of denser and thinner regions. Over billions of years, gravity drew material out of the thinner regions and into the denser ones, building up the bright filaments and clusters where galaxies gather and leaving the in-between spaces emptier and emptier. The voids are the result of that long drainage, the regions that gave up their matter to their surroundings and were left open and dark. Within the deepest voids, a world would find itself in a solitude almost beyond imagining. From such a place, the nearest galaxies would be so distant as to be barely visible, faint, scattered smudges across an otherwise empty sky. There would be no bright band of a home galaxy arching overhead, no crowd of close stars, only an immense and even darkness reaching in every direction. Any galaxies that do form within a void tend to evolve slowly and gently, undisturbed by close neighbors, living out their lives in near total isolation. It would be easy to read all this emptiness as bleak, but there is a steadier way to see it. The cold of space is not a force that reaches for warmth, not a wind or a presence, but simply the stillness that remains, where almost nothing moves. The voids are not hungry or hostile. They are the calmest geography the universe contains, places where nothing stirs and nothing is disturbed, an enormous and patient quiet that has held since long before any world began. There is a curious truth about cold that makes even the coldest place feel less forbidding. True absolute zero, the point where all motion would cease entirely, can never quite be reached, no matter how hard one tries. There is always a little motion remaining, a faint residual stir that cannot be removed, so that the coldest possible state is approached but never fully arrived at. The universe, left to itself, keeps cooling very slowly as it expands, the faint background warmth thinning further across the ages, edging always closer to that floor without ever touching it. It is a gentle thought that the cosmos drifts forever toward a perfect stillness it will never quite reach, always nearly at rest, never entirely so, holding the smallest trace of warmth, even in its emptiest and oldest corners. So we leave the coldest cloud and the great empty voids to their long silence, the universe at its most still and most spacious. There is a peace in such emptiness, the peace of a place that asks for nothing. And from the cold and the empty, we turn now to the worlds that drift without a sun and to the crushing dark inside the giant planets. Not every extreme place is a star or a remnant. Some are worlds, planets like the ones we know, but placed in conditions so harsh that they belong on this tour all the same. Two kinds of worlds stand out. There are the planets that drift through the galaxy with no sun at all, and there are the crushing depths inside the giant planets, where matter takes forms found nowhere on Earth. We tend to think of planets as bound to stars, circling them in steady orbits, warmed by their light. But the galaxy holds a great many worlds that have no star at all. These are the rogue planets, cast out of the systems where they formed, set adrift to wander the spaces between the stars alone. Some were flung away by the gravity of giant neighbors. Others may have formed on their own in the open dark. They travel the galaxy in perpetual night. There may be a remarkable number of them. Some estimates suggest that rogue planets could be as common as stars, or even more common still, billions upon billions of dark worlds drifting unseen through the Milky Way. Each one travels alone, with no sunrise, no seasons, no warm light to mark its days. Its surface would sit near the cold floor of space, frozen and dark, lit only by the distant stars scattered across its sky. And yet even these starless worlds are not entirely without warmth. A planet can carry heat of its own, left over from its formation and produced slowly within its interior. On some rogue worlds, that inner heat could be enough to keep an ocean of liquid water beneath a thick shell of ice, a hidden sea in the dark, warmed from below rather than above. It is possible that some of the most lightless places in the galaxy hold quiet oceans, sealed away beneath their frozen surfaces, calm and still. The other extreme lies not in the dark between worlds, but deep inside the largest planets themselves. Within a giant planet, the weight of all the gas above presses down with enormous force, and as you descend, the pressure and temperature climb without end. The familiar gases of the upper layers are squeezed into states that do not exist at any surface. Down there, matter behaves in ways our everyday experience never prepares us for. In the largest planets, the pressure becomes so great that hydrogen, the lightest and most ordinary of substances, is crushed into a liquid metal. This metallic hydrogen flows and conducts electricity like the metals we know, and its motion deep within the planet generates immense magnetic fields that stretch far out into space. The very center may reach pressures millions of times greater than the air at Earth's surface, and temperatures that rival the surface of a star. In some of the giant planets, the conditions may do something stranger still. Where carbon is present, the crushing pressure can compress it into diamond. Deep in those planets, it is thought that diamonds may form and then sink, drifting slowly downward through the dark interior. A slow and silent fall of crystal through layers no eye will ever see. The most ordinary pencil-lead carbon, remade by pressure into something rare, falling endlessly in the planet's depths. Finding these starless worlds is among the hardest tasks in all of astronomy, precisely because they give off so little light. A planet with no sun has nothing to reflect, and shines only faintly with its own dim warmth, if at all. The way we detect them mirrors the way we find wandering black holes. When a rogue planet passes almost directly in front of a distant star, its gravity briefly bends and brightens that star's light, and from the shape of that brief brightening, we can tell that an unseen, planet-sized object drifted across the line of sight. The galaxy, watched this way, appears to be full of them. What strikes many people most about rogue planets is the thought of their skies. On a world bound to a star, the day is ruled by that star's light, and the seasons turn with the world's path around it. On a starless world, there is no such day, only a perpetual night, lit faintly by the scattered stars and, perhaps, by a dim band of the home galaxy. The temperatures at the surface would settle near the cold floor of space, and the landscape, if any eye were there to see it, would lie in permanent twilight beneath an unchanging sky. The interiors of the giant planets offer the opposite kind of extreme, a place not of cold and emptiness, but of crushing pressure and heat. As you descend through such a planet, there is no solid surface to cross, only a gradual thickening of the gas, growing hotter and denser with every layer. Far down, the pressure becomes great enough to change the very nature of the materials, squeezing familiar substances into states that exist nowhere at any surface. The deeper layers conduct electricity, flow like liquid metal, and stir in slow currents that generate the planet's enormous magnetic field. The idea of diamonds forming and falling within these planets is among the gentlest images on this whole tour. Where carbon is present in the right layers, the immense pressure can compress it into the same crystal we prize as a gem, and these crystals, denser than the material around them, may sink slowly toward the center. It would be a silent, unhurried fall, a slow drift of diamond through the dark interior, going on for ages in a place no eye will ever witness, deep within a world far across the sky. The idea of a hidden ocean in the dark is gentler than it first appears, and it may be more common than we once thought. Even within our own neighborhood of worlds, there are moons far from the sun's warmth that are believed to hold liquid water beneath thick shells of ice, kept from freezing by heat generated within. The same may be true of starless rogue worlds drifting alone through the galaxy. A planet with no sun could still carry, deep beneath a frozen surface, a dark and quiet sea, warmed slowly from below, sheltered from the cold above by miles of ice. It is a strange and soothing possibility that some of the most lightless places in the galaxy may hold calm oceans in perpetual darkness, still and undisturbed, going about their slow chemistry far from any star, untouched by the long night outside. These are extreme places, the starless worlds and the crushing interiors, and yet they too settle into a kind of calm when we look closely. The rogue planet drifts quietly through the dark, perhaps cradling a hidden sea. The giant planet holds its strange interior in perfect, ancient balance, its diamonds falling slowly through the centuries. Neither reaches toward us. Both simply are, far away, doing what they have done for ages. And from these dark and crushing worlds, we turn now to the most extreme place of all, the one that everything came from. We have traveled to the densest, the strongest, the brightest, the coldest, and the emptiest places the universe contains. There is one more, and in a way, it contains all the others. The most extreme place in all of existence is not somewhere far across the sky. It is somewhere far back in time. It is the beginning of the universe itself, the first fire from which everything we have seen tonight was made. In the earliest moment we can reasonably describe, everything that now fills the cosmos, every star and galaxy and quiet world, was gathered into a space smaller than a single atom. It was unimaginably hot and unimaginably dense, and it was expanding with extraordinary speed. This was not an explosion within space, scattering matter outward into an empty room. It was the swift stretching of space itself, carrying everything along as it grew. In the first tiny fraction of a second, the universe is thought to have gone through a stage of sudden, enormous stretching, growing by a tremendous factor almost instantly. This brief and rapid expansion smoothed the young cosmos and set the gentle pattern of all the structure that would later form. Everything we see, every galaxy strung along the cosmic web, traces back to faint ripples laid down in those first moments of stretching. For the first slivers of time after that, the universe was far too hot for ordinary matter to exist. The particles we now think of as the building blocks of atoms could not yet hold together. Instead, there was a kind of formless sea, a plasma of the most basic particles, quarks, and the forces that bind them, flowing freely in conditions hotter than the center of any star that would ever form. The whole cosmos was a single furnace, with no inside and no outside, hotter than anything that has existed since. As the universe expanded, it cooled, and cooling allowed the first structures to form. Within the first few minutes, the basic particles combined into the first atomic nuclei, the cores of the lightest elements. The recipe set in those minutes still describes the universe today, mostly the lightest element, hydrogen, with a good measure of the next lightest, helium, and only traces of anything heavier. Everything more complex would have to wait for the stars. For a long time after that, the universe remained too hot and crowded for light to travel freely. The young cosmos glowed, but it was opaque, a fog of particles through which no clear beam could pass. Only after a stretch of time, on the order of a few 100,000 years, did it cool enough for the fog to clear, releasing the first free light into a now transparent universe. That ancient light is still traveling, stretched and cooled by the long ages, and it is the faint background glow we touched on earlier, the oldest thing the sky contains. This is the most extreme place we will visit, and it is also, in the most literal way, the source of everything gentle. Every atom in your body, every particle of the bed you are resting on, every breath you are taking, all of it passed through that first fire. The hydrogen in the water you drank today was forged in those first minutes. We are not separate from the most extreme place in the universe. We are made of it, cooled and scattered, and gathered again into something small and quiet and alive. The brief stage of rapid stretching at the very beginning solves several puzzles at once, which is part of why scientists take it seriously. It explains why the universe looks so smooth, and even on the largest scales, as if it had once been small enough to even itself out before being stretched enormous. It explains why space appears so flat and balanced. And it explains where the gentle pattern of all later structure came from, in the faint ripples laid down during that first swift expansion, ripples that would slowly grow, under gravity, into galaxies and clusters and the great cosmic web. The early plasma deserves a closer look because it is so unlike anything we know. For the first slivers of a second, the universe was too hot even for the building blocks of atoms to hold together. The particles that now make up protons and neutrons flowed freely in a kind of formless sea, bound to nothing, in conditions hotter and denser than the center of any star. Only as the universe expanded and cooled did these particles settle and combine, locking together into the first protons and neutrons, the first true matter, out of that primordial heat. The making of the first elements, in the opening minutes, set a recipe that the universe still follows. As the young cosmos cooled, protons and neutrons joined into the cores of the lightest elements, building mostly hydrogen, a good measure of helium, and only the faintest trace of anything heavier. That early balance still describes the ordinary matter of the universe today. Everything heavier, every atom of carbon and oxygen and iron, would have to wait to be forged later, inside the stars and in their depths, across the long ages that followed. The light released when the fog finally cleared is still with us, and it ties the whole tour together. For a few 100,000 years, the universe was too crowded for light to travel freely, glowing but opaque. When it cooled enough, that first light was set loose into a now transparent cosmos, and it has been traveling ever since, stretched and cooled by the long expansion into the faint background warmth we touched on earlier. The oldest light there is, the cooled glow of the first fire, still gently fills the sky in every direction. What makes all of this more than a story is that the universe left evidence of its first minutes, and the evidence agrees. The proportions of the lightest elements we measure across the cosmos today match closely what the early furnace would have produced, a quiet confirmation written into the makeup of ordinary matter everywhere we look. And the faint background light that fills the sky carries within it the gentlest ripples, tiny variations laid down in those first moments, the seeds from which all later structure grew. We did not witness the beginning, and we never could, yet the universe kept a faithful record of it in the abundance of its elements and the soft patterns of its oldest light. That such an extreme moment should leave behind so calm and so readable a record is its own kind of reassurance, a sign that even the wildest beginning settled into order we can understand. So the most violent place in all of existence turns out to be the cradle of all the calm that followed. The first fire spent itself long ago, cooling into stars, into worlds, into the soft dark of an ordinary night. You are a small ember of it, resting now, warm and whole. And with that, we come to the last stop on our tour, the edge not of space, but of what we are able to know. Our final stop is not a place in the ordinary sense. It is a possibility, an open question that sits at the very edge of human understanding. It is, in a way, the most unsettling idea in all of physics, and it is also, when held correctly, one of the most peaceful. It concerns the nature of empty space itself, and whether the calm we take for granted is as settled as it seems. We tend to think of empty space as simply nothing, an absence, a blank background against which everything happens. But our science suggests that empty space has properties of its own, a kind of underlying energy, a state in which it rests. And there is a question, still unresolved, about whether that state is the lowest and most stable one possible, or whether space might, in principle, be resting in a state that is merely stable for now, with a deeper calm beneath it. If space were resting in such an in-between state, then in principle, it could one day settle to its true lowest state, the way a ball perched in a shallow dip might eventually roll down to a deeper one. This is one of the open questions at the far edge of physics, a possibility raised by our equations that we cannot yet rule in or out. It lives at the meeting point of the very large and the very small, exactly where our theories are still incomplete. It might sound like something to worry about, but consider its nature carefully, because the details turn it gentle. Such a change, if it could happen at all, would spread at nearly the speed of light. That means there would be no warning, no sign, no slow approach to dread. It could never be seen coming, and a thing that can never be seen coming is, by its very nature, nothing to watch for. There is no vigil to keep, no preparation to make. It is the one possibility that cannot trouble a single quiet evening. And there is far more reason for calm than for concern. As best we can tell, the state of space has held steady for nearly 14 billion years, through the forming of every galaxy and star and world, including our own. Whatever its deepest nature, it has been remarkably, patiently stable for the entire history of the cosmos, and all evidence suggests it will remain so far beyond any horizon that has anything to do with us. The universe has rested in this calm for ages and goes on resting. What this question really offers is a reminder, and a gentle one. It tells us that even now, after everything we have learned, the universe still keeps a few of its doors quietly closed. There are still edges to our map, still places where the known fades softly into the unknown. We have lived our whole history alongside such edges, and we have slept soundly beside them. Not every mystery is a warning. Some are simply the universe admitting, kindly, that not everything has been decided. To understand why this question even arises, it helps to think of stability in terms of a ball resting in a valley. A ball at the bottom of the lowest valley is perfectly settled, with nowhere lower to go. But a ball resting in a shallow dip higher up is only settled for the moment, since a deeper valley lies somewhere below it. The question physicists ask is which kind of resting place the energy of empty space occupies, and our current understanding is simply not complete enough to say for certain. It is an honest gap in our knowledge, not a looming shadow. The most reassuring feature of the whole idea is how it would unfold, because it removes any reason for worry. If empty space could ever settle to a lower state, the change would spread outward at nearly the speed of light, which means it would arrive without any warning at all. There would be no slow approach to watch for, no gathering sign, nothing to anticipate or dread. A possibility that can never be sensed in advance is, by its very nature, not something that can disturb a life, or a night, or a single quiet thought. And the weight of evidence points firmly toward calm rather than concern. As far as we can measure, the state of empty space has held perfectly steady for nearly 14 billion years, through the forming of every galaxy and star and world, our own included. Whatever its deepest nature, it has proven remarkably, patiently stable across the entire history of the cosmos, and everything we know suggests it will remain so for spans of time so enormous that they have nothing to do with any human concern. What the question really leaves us with is a gentle humility. It reminds us that even now, after all we have learned, the universe still keeps a few of its doors quietly closed, a few edges where the known fades softly into the unknown. We have lived our whole history beside such edges, and we have rested peacefully next to them. There is no need to force every door open tonight. It is enough to know they are there, and to let them be. There is a final comfort folded into this question, and it ties the whole tour together. The long stability of empty space is not a small thing. It is the very condition that made everything else possible, the steady ground on which galaxies formed, and stars ignited, and worlds gathered, and life arose. The calm of the universe is not an accident we happen to be enjoying. It is the same calm that allowed us to exist at all, holding steady across nearly 14 billion years, so that something small and aware could one day open its eyes within it. The deepest uncertainty at the edge of physics turns out to rest upon the deepest reliability there is, a quiet that has held through all of cosmic history and that holds, gently, around you now. So we let this last question rest where it belongs, at the far edge of what we know, unsolved and untroubling, a door left softly ajar in the dark. There is peace in that, the peace of not needing every answer tonight. The universe is large and old and full of quiet mysteries, and it has held us gently through all of them. And so we come to the end of our tour, having traveled to the most extreme places the universe has ever made. We have stood, in the mind, on the densest ground and beside the strongest magnet, beneath the brightest engines and within the coldest dark. And we have found, at every stop, the same quiet truth. The most fearsome places in the universe are also the most distant. They turn far away, indifferent and unreaching, and every one of them helped to make the calm world where you are lying now. The neutron stars are still spinning. The black holes are still turning. The first fire long ago became the soft dark of this ordinary night. Let the distance hold them all. Let your breathing slow. Let the night settle over you like the quiet between the stars. Sleep well and good night.